Yeah, cool. So yeah, thank you. And you're just making sure everyone can see my screen and all that, correct?
I can see it. If anyone can't see it, shout now.
Okay, great. Yeah, sounds good. Okay, so hi everyone. Yeah, so my name is Vivian Rindesbacher, and I'm a PhD student at UC San Diego. And I'm really excited to tell you all about some work that been doing with some folks at UCSD on verifying the Tock kernel. Okay, so like what is Tock? Well, Tock is an embedded operating system that's designed to run multiple applications on microcontrollers. Now, Tock is used in industry by companies like Google and Microsoft, and it's also used by some smaller companies like Oxid OS, which is an automotive startup. Now, Tock is similar to many classic OSes like Linux in the sense that it's made up of a kernel. There are drivers, which are known as capsules in Tock, and then there are also processes or applications. Now, Tock is different than classic OSes in a few ways, but one exciting way that I sort of want to mention right up front is the fact that it's written in Rust. Okay, so let's go over a little bit of Tock's operating system design. So at the most basic level, we have actual hardware. And so this is going to have things like a CPU. It's going to have, a timer or alarm hardware. We'll have GPIO pins, and some other hardware modules. Now, this hardware really provides the fundamental capabilities that are needed to build and run software components. To make this useful to applications, which we'd obviously like to write at a higher level of abstraction, right? We don't want to actually like deal with all the, configuration and setting all the bits in this hardware. The kernel is going to create some useful abstractions of the hardware to provide critical services. So for example, we might have an abstraction over the alarm or the timer hardware so that we can build something like a scheduler, right? To run applications in a preemptive manner. The kernel is also going to provide other critical services like managing memory for applications. And so, it might provide something like a syscall interface so that applications can request services of the kernel, right? For example, requesting more memory. Okay, the next component of Tock is capsules or drivers, as they're known in classic OSes. And capsules are going to run at the same level as the kernel, so in something that we call, like quote unquote kernel space. Now, these aren't too different than standard drivers. So for example, you might have a timer driver which exposes a virtual timer to applications via the syscall interface. Now, one thing that I really do want to mention here, and I think is pretty interesting, is that capsules differ from standard drivers in the sense that they're not allowed to access hardware directly. So if a capsule wants to sort of deal with, underlying hardware, it has to do so through a safe abstraction that's provided by the kernel. So now the final component of Tock is applications or processes. And these will run in user space, and they can be written in arbitrary languages. And at a high level, they're just very similar to standard processes or applications, in an OS like Linux. Okay, so Tock is explicitly built with safety in mind. And one of the most important properties that Tock wants to enforce is something called memory isolation. So what is memory isolation? Well, broadly, memory isolation means that OS components should be isolated to their own regions of memory, okay? And just as an example, if I have a process, that process really shouldn't be able to access another process's memory or something like kernel or capsule memory. And so like, why do we care about this? Well, if there's just one malicious application, right, and we don't have memory isolation, well, that application could do things like steal secrets from other processes, corrupt memory, or maybe even crash the kernel and the entire system, right? Okay, so how does Tock sort of achieve memory isolation? Well, earlier I mentioned that, hey, this thing is written in Rust, okay? And so the kernel is going to rely on the type and memory safety guarantees of the Rust programming language to give us some memory isolation. Now, there is some unsafe code going on here, right? We do have some unsafe Rust because we do have to deal with hardware. but use of unsafe Rust is pretty restricted throughout the Tock kernel. Okay. Now moving up to capsules, one thing that's really cool, I think, about Tock is that capsules are restricted to being written in entirely safe Rust. And this goes back to what I mentioned before, where capsules cannot deal with hardware directly, right? So anything to do with hardware has to be done through a safe abstraction that's provided by the kernel. And so here we have very strong type and memory safety guarantees from the Rust programming language. Now, the last component is processes, right, or applications. And the question is, like, how do we do this? How do we enforce memory isolation for processes? Because they're written in arbitrary languages, right? So for example, a process could be written in C, and there we can't rely on any language level features for memory isolation. Okay, so the classic way that this is sort of done in an operating system like Linux is via hardware, right? And something called a memory management unit. So usually every process, right, in an operating system has its own virtual address space. And this hardware, this MMU, takes care of translating virtual addresses into physical memory addresses. Now here, because we're in the microcontroller world, there is no virtual memory, right? Everything is physical. So an MMU just, first of all, doesn't exist, and second of all, wouldn't be useful. Now, Tock still does use hardware to enforce memory isolation, and specifically, it's going to use something called a memory protection unit, or MPU. Okay. Now, what an MPU does is it basically gives you a way to guard access to memory. Okay. Specifically, it allows programmers to specify different regions of memory and then to configure those regions with something called attributes. Now, these attributes are basically just things like access control permissions for a specific region. So I can specify a region of memory as like read only or read execute or read write. Okay. So in Tock specifically, the MPU is going to be turned off in kernel space. And that's because the kernel needs to do things like, manage process memory. And again, we're, relying on Rust to keep us safe here. Now, when we want to go ahead and run a process, what's going to happen is that the MPU is going to get configured by the kernel, and then it's going to be switched on. And specifically, what we're going to do is we're going to configure the MPU to allow read and execute access to the process code, which is in Flash, and read and write access to the process stack, data, and heap. Okay, so now the question becomes like, okay, if we have, these sort of like type and memory safety guarantees at the kernel level, right, in kernel space, and we add some memory protection in user space via hardware, like, can we dot the I's and cross the T's and throw our hands up in victory and say like, hooray, we've done it. We have memory isolation across the entire operating system. And as you can guess from the subject of this talk, what I'm going to talk about today is how this can go wrong, right? And I'm going to talk about why we're, verifying the kernel, specifically in relation to memory isolation. Okay, so for the rest of this talk, what I first want to do is sort of paint a picture of what goes wrong, right? And why are we actually verifying the Tock kernel in general? Okay, and then I want to move to, sort of giving a high-level overview of the verification that we're doing. Okay, so as I mentioned before, Rust with MPU protections is still not enough. And the fundamental issue here is that MPU configuration code is susceptible to bugs, and specifically, it's susceptible to bugs where Rust doesn't help us. Okay? Similarly, there are these things called interrupts, right, in operating systems. And unfortunately for us, interrupts are written in assembly in the Tock kernel. And so here we have no language level guarantees, right? And so the important thing to understand here is that these bugs, so bugs in MPU configuring code and interrupt handling code, can and do break memory isolation. Okay. So I want to give you, sort of like a real example of a bug that breaks memory isolation. And this bug is going to be in MPU configuring code. Okay, so below I have this trait method called configure MPU. And as you can probably guess from the name, this method is used to configure an MPU for a given process. Okay. Now I've sort of like highlighted one of the parameters here, right? This config thing. And the important thing to understand here is that this configuration has all the regions and corresponding attributes that have to be configured for this process to run. Okay, so let's take a look at what this configuration looks like. Well, it has this, sort of field called regions, and this is a fixed size array, and the size here is 10. Now, the reason this is because the MPU in this particular case has a total of 10 configurable regions. Okay, and a really important thing to understand here is that the process might not need all of them. We might not need to use all of the regions available in the MPU. And so we're going to use an option type to denote this. So if you look at the type definition of this field, like if we need an MPU region, then the slot in this array is going to be some. And then if we don't need it, it's going to be none. All right, so let's jump into like the actual body of this trait method. So the first thing we're going to do in configuring an MPU is we're going to iterate through the total possible number of regions in the configuration. And then again, since the process might not need all the regions, we're going to match on the given region. Okay? Now, if we do need to configure this region, we're going to go ahead and configure the MPU, okay, based on the start address and the size and the attributes that we need for that region. And then if we don't need this region, right now we're doing nothing. Okay. So before I sort of talk about what the bug is, I want to sort of go through like what the ideal scenario is. What is the actual behavior that we want from this function? Okay, so you can imagine that if I'm running some process, and let's call it process A, right? I'd like the MPU to be configured in such a way that I have read and execute access to the process code, and then read-write access to the process stack data in heap. Okay? And then if I switch to running another process, right, let's call it process B, I would like the MPU configuration for process A to be totally replaced, right, by a new configuration that allows read and execute access to process B's code and read-write access to process B's stack data in heap. Okay. And so now I sort of want to ask the question, well, like, okay, so what if process A uses all of the regions of the MPU, and then consequently we run process B and we use like 9 out of 10, let's say. Well, it turns out that, this code was being relied on to overwrite the entire MPU configuration. And so in that case, what happens is something like this, where yes, I have read and execute access to process B's code, and I have read-write access to, process B stack data in heap, but I also have access to a leftover memory region that, is process A's memory. And so this is just like a flagrant violation of memory isolation, right? Because now as process B, I can go and like, do things like read process A's code, or maybe if it was a different region, read its stack or heap, right? Which is bad. Okay, and so it turns out the fix for this is like super simple. It's like 4 lines of code. And it's just to invalidate regions that aren't used by this MPU config, so we don't have any left over from a previous process. Okay, so now this is like an actual bug that was found in the Tock kernel. And it's not like, this was around for like a day or a week. This was actually present for 2 years. Okay, so a significant amount of time. And just to like really drive this point home, this isn't like an isolated incident. This actually happens again and again and again, right? Bugs in MPU configurations have broken memory isolation many, many times. Okay, so our approach to sort of like addressing this problem, of course, is verification. And so I want to sort of go into what we're doing from the verification side. All right, so what do we actually want to verify? Well, our goal is to ensure that memory isolation for processes isn't broken. And there are multiple parts of the kernel that are important for this. So very intuitively from the example I showed, right, code dealing with MPU configuration is something that we need to get right, okay? It also turns out that code dealing with interrupts is something that we need to get right. And later on in this talk, I'm going to go through, the reasons that we think it's important to verify interrupt handling code. And now our approach is to use Flux to verify these kernel components. Now, Flux is a refinement type checker for Rust that plugs really nicely into, the Rust language ecosystem. And if you're interested after this talk, and maybe Nico or Ranjit, you guys can plug some Rust resources in the chat. There's a paper from PLDI in 2023. There's also, we have a Flux book, and then we have a Zulip chat, where you can come and ask questions about using Flux. So definitely, encourage you to check out those resources. All right, now before I get into like the sort of high level overview of our verification, I want to give everyone like a very, a quick demo of how Flux can be super useful. So I'm going to switch over to VS Code, hopefully. And can you guys see VS Code now?
Yes.
Okay, fantastic. And is the font big enough? Should I blow it up a little bit more? How does it look?
For me, it's fine.
Okay.
Yes.
Yeah, I think if anyone thinks it's not big enough, just yeah, shout at me and I'll go ahead and blow it up. Okay, so what I've done here is I've sort of like extracted some pieces of code from the actual Tock kernel. And there's a lot going on, but I just want to focus your attention on two things. Okay, the first is the struct here, okay, called MPU. And this is the software representation of the actual MPU hardware. Now, one thing that's really important here is that it has this const generic min region size. And if you look down at this, trait method, it turns out that this const generic is being used, to implement some logic. Okay, so before we sort of go into any more detail about this, let's just run Flux on this code. Okay, so I've done that with this command cargo flux, and it's super simple to do. And immediately I've already seen an error, right? And that error is, hey, on line 51, there's a possible remainder with a divisor of 0. And so indeed, if I go to that line of code, what I see is that we're using min region size with a modulo operator. Now, what Flux is yelling about here is that if min region size is 0, this code is going to crash, right? I will have a divide by 0 error and I'll panic. Okay, so that's kind of cool, right? Like Flux has already caught something that we've done wrong. And so now, like as a programmer, right, I want to get rid of this error, right? So there's two things that I could do. First, I could check, if the min region size is actually valid by, adding an if statement, for example, that checks like, hey, is this greater than 0? And if so, return an error. Now, that's great, and I think, I probably would do that, but I also want to enforce something like this statically. And unfortunately, the Rust type system can't really do that for me because there's no way to introduce a bound on a const generic. Now, luckily, Flux is going to come to the rescue here, and I just want to show you how easy it is to do something like this. Okay, if I just add this little annotation here, I add this invariant, and the invariant is going to be that, hey, the min region size here should be greater than 0. Now, this error should just go away. Hooray. Okay, awesome. And so now just to show you that like Flux is going to enforce that this invariant is upheld across the entire code base, right? So anything that uses MPU, if we go down here and we, sort of uncomment my use MPU function, which is instantiating an instance like of MPU with min region size is 0, right? If we go and run Flux now, what we'll see is boom, right? Flux says, nice try, buddy. Like you can't do that because you told me there's an invariant on this const generic, and then you tried to violate that invariant, right? And so the point here that I just want to like emphasize is just that Flux gives you really nice, easy ways to, first of all, find like bugs in your code, and then secondly, enforce invariants across your code without much work. Okay, I really quickly just want to show a second example here because it is relevant to our work in the Tock kernel. So here again, I've pulled some MPU configuration code out, and this has to do with regions. okay, with MPU regions. And before we do anything, I'm just going to run Flux again. Okay. And here again, right, on line 47, Flux is screaming at us and it's saying, hey, there's an arithmetic overflow issue. Okay, and if we go check this out, I'll just explain what the issue here is. If you look at the implementation of log base 2, log base 2 of 0 is actually 0. Okay, and so then 0 minus 1, right, because the resulting value is an unsigned 32-bit integer, this will actually be U32 max. Okay, and this is bad, right? Just like plainly looking at this code, but in Tock, right, in the context of Tock, this ends up being exponentially worse. And the reason that is because size value is actually used to write to the MPU. So we're going to configure the MPU with size value. And if you write U32 max to the MPU, you're basically giving a process access to the entire system address space, which is just an absolute disaster. Okay. So now switching back to my slides, I just want to, show you like, yeah, this was an actual bug that we found in Talk. Um, there was an underflow issue and a modulo issue that basically, if it could be exploited, would give you access to the entire system address space. And I just think it's really cool that like Flux can catch this with no specifications at all, right? Okay, so now I want to move on to some high level detail about the verification that we're doing in Talk. Okay, so I want to go back to the configure MPU method that I showed before, in particular, in the bug example. And the question that I want to ask here is like, okay, so how can verification actually help us with this method? Well, if you really think, like deeply about it, there are really two things going on here. We first have the actual hardware, right? So the actual MPU state. And then we have a process-specific configuration. Okay, and so both of these are going to have things like regions and corresponding attributes for the regions. Okay, and what our specification should really say is something about how the configuration relates to the actual hardware state. Now, this is exactly what we've done. Okay, and so there's a whole bunch of like Flux syntax on your screen now. But I think that the most important thing to grasp is that when we say like this ensures thing, this is really just specifying a post condition. Okay, and in our case, what the post condition is going to say is that, hey, there's a one-to-one mapping between configurations, okay, or the configuration for this actual process and the actual hardware. Okay. And that is expressed very intuitively here, where we basically say, hey, for every possible MPU region, the region configured in the MPU matches the region that we want in the configuration. And also the attributes for that region match exactly between the MPU and configuration. So now let's say that like I make a mistake, right? I forget to configure region 7, or I do something similar to the bug that I showed earlier. Well, Flux is going to catch this, right? And in particular, it's going to be like, oh, like wait, hold on, dude, slow down. I can't prove this post condition, and in particular, I can't prove that this region 7, matches what you specified in your configuration, right? And so with this type of verification, right, we're going to be able to catch and fix bugs like the one that I showed you earlier. Okay, so that's just like kind of a small, example for one function that deals with the MPU, but we really want to verify all of the MPU functionality. And one key thing to understand here is that like Tock is a multi-platform OS, and that means that there are different architectures that it supports. And so because of that, the MPU that it has to deal with for each different architecture is gonna have different semantics. Okay. So a very intuitive way to sort of approach this, right, like in Rust, is to have something like a trait, okay, that implements, some interface specifically with some methods, right, to do certain operations on an NPU. And then I can go and implement that trait for each differing architecture and sort of, do all the domain specific things that I have to do to configure a specific NPU. Okay. And it turns out like this is exactly what Tock does. Okay. So Tock has a trait NPU that's implemented for each different architecture, and it has a whole bunch of methods and configure NPU, which I've talked about, sort of like quite a bit in this talk, is one of those trait methods. Okay, so let's take a look at this NPU trait. Again, it's generic, right? And it's generic on this associated type NPU config. And this, again, is going to be specific to the architecture that I'm implementing this trait for. And then it's going to have a whole bunch of methods, such as enable app NPU, which enables the NPU for user space apps. Now, from a verification perspective, what we want to do is we want to provide a specification for each of the methods in this trait generically. And we want to do it generically because we don't know what it means for the NPU to be enabled until we know what architecture we're actually dealing with. Okay. Luckily, there's a feature in Flux called generic associated refinements that allows us to do this sort of modular verification. So in particular, two things have sort of popped up on the screen. The first is like this generic refinement enabled, okay, which is sort of something that we haven't defined yet because again, we don't know what it means for an NPU to be enabled. But if you look at now the signature of enable app NPU, you see that there's this post condition that uses this associated refinement enabled, as like a logical predicate. Okay. So now if we jump to an actual architecture specific implementation, what we're going to see is something very similar to, what you see with like Rust trait development in general. The enabled generic refinement now has a concrete implementation. And in particular, we're saying something about, the control register for the NPU, because that's what it means for like this particular architecture's NPU to be enabled. And then if you look at enable app NPU, nothing has changed, right? We're using the exact same post condition, but now because there's a concrete implementation for our generic refinement, and then also for the enable app NPU trait, method, right? Flux can now check that enable app NPU adheres to the specification, right? So that the NPU is actually enabled after this function runs. Okay, so I personally think like this is a really nice feature because it allows us to verify the NPU code as is. So this, like the code that I just showed you is literally the Tock code. And it's also literally, sort of like the specifications that we added to that Tock code. And so, one of the things that you run into when you're doing this sort of like retrofitting verification thing where you're trying to verify something that wasn't built for verification in the first place, right? You feel like you constantly have to change code to get verification to work. And in this case, we're good to go. We don't need to change anything. The other thing that's nice about this is, it's sort of modular, right? It lets us verify cross-architectural code that deals with the NPU in a very similar style as, like is being used to actually write the code in the first place. All right, so that's sort of our approach for talking about, things like configuring the NPU or enabling the NPU. But if you think about it, right, we haven't really tied that back to process isolation yet. Right? And so our ultimate goal here is going to be a proof that processes can only access their own memory. And so what we need to do now is we need to tie, this code that does things to the NPU, like enable it or configure it, we need to tie that back to the process memory layout so that we can say something like, hey, when we call this function, we can guarantee that, a process can only access its own memory. Now, we're still working on this, so this isn't totally done, but I do want to give a high-level overview of our approach because I think it is pretty intuitive. Okay, so I want to start with the struct process standard. And this is the software representation of processes that's used by the Tock kernel. Now you can immediately see that there are some super relevant fields. Okay, so in particular, we start with, some fields that track the app's memory size, right? We have a pointer to the start of memory for a process, and then we can also easily compute the end of memory for a given process. We also have the process flash, right? So we have a reference to where, the process's code is. And then we have some NPU configuration and regions. And here our job is going to be to make sure that these reflect the actual memory layout, right? So that these, sort of like cover the space that's actually taken up in memory by the application. All right. So now I told you before, right, that at some point the kernel decides to set up the NPU for a process. And so, of course, there's going to be a method somewhere to do that. And here is that method, right? It's called setup NPU. And basically all it does is use the current configuration or NPU configuration for a process to configure the NPU. And like, hey, look at that. This is the function or trait method that we added specifications for before. And so here we're going to have a precise idea of NPU state from our specification of configure NPU. And using that, we can add a specification to set up NPU that explicitly talks about the NPU's current configuration in relation to flash and the stack data and heap for a given process. Okay, now just digging down into like the last level that I want to talk about. At the very beginning of this talk, I said, hey, when the kernel decides it wants to run a process, what it does is it sets up the NPU for that process, and then it turns the NPU on, and then it goes off and decides to run, the actual process code. And so if you dig deep enough into the Tock kernel, what you'll find is that there is a function that does exactly this. And it's called doProcess. Okay. And as you can see, it sets up the NPU using the method that we just saw. And then it calls one of our trait methods, enable app NPU. And so here again, because we've sort of verified these functions, we have a precise idea of what the NPU state is from those specifications. And so that's going to allow us to add a specification to doProcess that ensures first that the process can only access its own memory and nothing else. And second, that the NPU is actually enabled. And if Flux, basically gives us the green light and can prove that this is indeed the case, right, then we're good to go, right? We can kind of guarantee, oh, great, my NPU is going to be turned on, and this process can only access memory that it's supposed to. Okay, so that's sort of the high level of verifying NPU configuring code. And now I just want to wrap up with sort of talking about, our verification for interrupts. Okay, so interrupts in Tock, again, are written in inline assembly. And so this is unfortunate because they're part of the kernel, right? And we'd like to have some language level guarantees about, type and memory safety. And unfortunately, we don't. And to sort of compound the issue, it's not like these, interrupt routines are sort of adding 2 + 2. They're actually doing very, very unsafe things. Okay, so for example, they write to memory and they set and save hardware registers, right? So this is kind of scary. And really the thing that makes matters infinitely worse is that interrupts can run at any time, such as when you're configuring an NPU. So you can imagine like I'm in the middle of my configure NPU loop and some like peripheral in hardware decides to trigger an interrupt. And all of a sudden, I'm going to branch from my NPU configuring code off to like some interrupt handling routine, right? That's running a bunch of assembly that's doing things like writing to memory and setting and saving hardware registers. And then we're going to come back to our NPU configuring code and continue running it, right? Like that's kind of a scary proposition, in my opinion. And so what we really want to ensure is that like critical memory or hardware state isn't getting clobbered in a way that can mess with things like configuring an MPU. All right, so what do we actually want to verify? Well, we want to verify that our CPU state doesn't change too much when the kernel is interrupted. And too much is in a way that sort of like clobbers hardware registers or changes a stack pointer, right, in a bad way that, will cause us to either crash or sort of like execute on nonsense when we come back to the kernel. The other thing is that memory shouldn't change too much when the kernel is interrupted, right? And so we're going to be very, very specific about what all these things mean. But first, I want to sort of go through like, okay, how are we actually verifying assembly in the first place? Okay, so verifying assembly is hard. Like, unfortunately, I don't think anyone really wants to do this. And there are kind of like a limited set of tools available to reason about assembly. Now, luckily for us, we're sort of saved by a key insight. And that insight is that to verify Tock's interrupt handlers, we only need a very, very small subset of instructions. Okay. So for example, on the ARM hardware, so the ARM architecture, Tock has four different interrupt handlers. And across all four of those interrupt handlers, there's like 22 different instructions that are used. The other bit is like hardware just in general these days is like super, super complicated, right? And so we'd have to like model a bunch of things, right? Like a bunch of bits and how they change with different operations. But luckily for us, we only really care about hardware interrupt semantics. We don't necessarily care about every single aspect of the hardware. And that actually makes our job a lot easier. Okay, so what are we going to do? Well, our approach is to model an operational semantics for assembly. And the way that we do this is we basically write an emulator in Rust, and then we add specifications to that emulation. Okay, so we're going to do this step by step. The first thing that we're going to do is we're going to find a representation for hardware in Rust, and then we're going to sort of implement the semantics that hardware has for interrupts. Then we're going to implement and add specifications for the actual assembly instructions that we need. And then using those instructions, we're going to be able to lift the entire interrupt handling assembly to Rust, right? And we're also going to be able to add specifications. And then once we have all these components, we can actually model the entire interrupt flow. So we can pair the hardware semantics, with the actual assembly routines themselves, and come up with like a nice proof about what these interrupt handlers are actually doing with respect to the hardware. Okay, so we start with our sort of CPU representation, and this is just a a struct that has some fields and it has some things like general registers, has a stack pointer, and it you can imagine it has memory and all sorts of other things. Okay. Then using that representation, we can start to implement instructions. And so here is like some function called move word immediate. And basically what it does is it moves a word size value into a given register. And so we go ahead and we implement all that functionality. In Flux, it's sort of like a standard thing that you do when you're writing an emulator. But then we can add, a specification. And here we have a post condition that basically says, hey, after this function runs, okay, the register that we wanted to update will now contain the value, and the rest of the CPU state is going to be unchanged. Every other field in our CPU struct is going to be exactly as it was before. And Flux is actually going to check that, like, hey, this specification, this function is implemented in a way that adheres to the specification. All right, now I want to show you, an actual interrupt handling routine uh, from Tock. And like just a warning, like please don't try to read any of this. The point that I just want to get across is that we have this thing that's like in this global ASM macro, and it's just a bunch of like, it's like a string, right, that has a bunch of assembly routines. And so like this isn't really nice to think about. But what's great is that we can just like lift it to our emulation, right? And so now this is just like a function. Okay, so this is the systic interrupt service routine, right? And the function is just basically us calling all the instructions that we've lifted to Rust via emulation. Okay. And now here again, we can add a specification that talks about exactly what this, assembly is doing to the hardware. Okay, so in particular here, we have something about CPU post-systic ISR, which basically says, oh, hey, this is exactly what's going on when you run this assembly. Okay. And so now, since we have, all this lifting, we can basically model the entire interrupt flow. Okay, and so this is exactly what this function preempt is doing. So in particular, I just want to go through this step by step. We start by doing something called hardware stacking. And this is, some basically hardware specific functionality where the hardware decides to be nice to you in the case of interrupts and save certain registers onto the stack automatically. Okay. Then we're going to go ahead and call our ISR, right? And this is like the actual, interrupt code that's been written by the Tock developers, but just lifted to our Rust emulation, as I just showed you. And then the last thing that we're going to do is, again, hardware specific, and it's hardware unstacking. So basically restoring all the registers that were previously saved. Okay. And then here, right, we need like basically a proof about the CPU state being valid after an interrupt. So let's sort of think through like what the specific things that we need to make sure hold true are. Well, for one thing, the registers can't change, right? And I sort of like alluded to this before. And so the reason they can't change is because if I'm, doing a bunch of operations with these hardware registers to configure an MPU, and then I go off to interrupt land and run my interrupt service routine and change one of the registers, when I come back to, the MPU configuring code, things are just going to go wrong, right? I might write a baloney value to like the MPU itself, so I break process isolation, or I like crash the kernel entirely. Okay. Now the same thing is sort of true for like the kernel stack pointer, right? If I think my stack pointer is pointing to like memory address A, but it's actually pointing to memory address B, all sorts of things can kind of go wrong. And then the last thing is that like very specific bits in memory should change based on these interrupt service routines sort of running. And we just want to make sure that it's not overwriting anything that it shouldn't. And so, I've sort of listed those things, but I think we can sort of skip going over those for now. Okay. So that's, most of the work that we've been doing from the verification side. And I sort of just want to conclude, with what we found so far and then some challenges in future work. And then I think we can wrap up with some questions. So far we have found actually a bunch of bugs um, in the Tock kernel. And so we found, a few that have to do with the actual interrupt service routines. And then we've also found some bugs in the actual MPU configuring code. And so it's been like pretty cool that an effort like this has yielded like real results. And I think all but one of these actually does break memory isolation. So I think we're making good progress on making a meaningful impact. Okay, so in terms of challenges, one of the things that's been difficult about this is sort of trying to like retrofit verification into something like a pretty big project that wasn't built for verification in the first place. And so one thing that we found is that like Tock uses many Rust features liberally. So we saw, use of associated traits with the MPU configuring code. I showed you an example of const generics, and like it's actually really relevant because there was a potential bug that had to do with that. And then, Tock also uses trait objects all over the place. And so, Flux has to support all of these. And it turns out that it's like really not that easy to do. And so, we've really been working closely with Nico, who's on this project, on making sure that Flux can actually handle all of these features. And just like a little shout out, some of these are like really hard to do. And so, like the support that Flux has for associated traits was actually a POPL paper this year, right? So some of this stuff is really difficult to actually do. All right. So just like last thing I want to go over, some future work. So as I kind of showed, we want to tie process code into MPU configuring code so that we can have an ultimate proof about what memory regions a process can access. Another thing that we're sort of thinking about, very actively is something called direct memory access or DMA. And I really don't want to go into this in too much detail. Just the thing to understand here is like this is totally independent of the CPU and the MPU. And because of that, it ignores the MPU configuration entirely. And so we need to make sure that like DMA doesn't break any of the invariants that we care about with respect to memory isolation. Okay? And then the last challenge I think we sort of have is that we need to test our specifications. So, as I'm sure you've noticed throughout this talk, a lot of what we're doing is modeling hardware, right? And so it's definitely possible that we've gotten, a spec wrong somewhere. And so, I think we really want to come up with a way to test our specifications so that we have a high degree of confidence in the work that we've done. But I think that's all I sort of want to go over today. And I think we have around like 10 minutes for questions. So yeah, I guess we can pass it back to Johannes or anyone that has some questions.
Yes, thanks a lot for the talk.
Yeah.
Does anyone have questions? I guess Brian has a question, so go ahead and start.
Yeah, thanks for the talk. I was curious, were there places where you ran into like the restrictions that refinement types impose, like where you couldn't specify something the way you wanted to, or you had to work around that? Or has it been pretty smooth?
Yeah, so it's been pretty smooth for the most part. I think we've definitely had challenges with like just like features in general. I think one thing that I would say here is like we're not actually verifying properties that are like that complex, right, in Tock. Like I think a lot of the properties are pretty straightforward. The thing that is difficult is just like all the machinery that you need to actually talk about these things. And so I think like for the most part, it's been fairly restricted to just like supporting all the like language features that Talk uses. But I think refinement types have been like honestly pretty great so far.
Okay, cool. Glad to hear it.
Yeah.
Okay, next question by Liao.
Hi. I'm wondering about the scale of this project. How big is Tock and how much of it do you plan to verify?
Yeah, so that's a great question. So I can't remember the exact details of how big Talk is, but I think the kernel is somewhere around like 12 to 20,000 lines of code. So it is fairly big. But again, our verification is sort of isolated to different components. So specifically, we're verifying, all the implementations of that MPU trait that I showed. We're also verifying like the interrupt assembly, which is a very small component. And then, I think where we're unsure right now on like how much we need to verify is tying sort of like the MPU configuring code together with the process specific memory layout. And so we'll see how much code that is. I think it may be like quite substantial, but I'm honestly not sure yet. Cool. I think we have another question as well.
Yes, sure. Sasha, you can ask.
Yeah. First of all, that was really cool. Thank you.
Yeah, thanks.
And second, you said like you want to test your specs that you've written.
Yeah.
If you had a plan for verifying them instead,
Hmm.
what path would you take? Do you have an idea?
I can't say that I do right now. I think we've been like pretty in the weeds on the actual verification bit, so I haven't thought too much about it. I guess like Yeah, I'm not sure how I would verify the specifications, to be perfectly honest. But I mean, if you have some ideas, you know, you can shout them out.
I don't have anything that would
Yeah.
probably work, but I mean, I have ideas, but that's my second question also is
Yeah.
how long does like how fast is I remember Flux being extremely fast when Nico presented it in
Yeah.
2023 or something.
Yeah.
How fast is it on that big code base now that you have an actual, big
Yeah.
example?
Yeah, it's actually like pretty quick. I think we can run like and check all our sort of specifications in less than 20 seconds. Which is great. We have ran into some issues on the like interrupt side with all that specifically, and I think what that sort of came down to was like, everything there is sort of like reasoning about bit vectors, and SMT solvers sort of hit some like performance issues when you get into that land. And so we've done like a bunch of optimizations, and I think that actually has made Flux better in general. But so yeah, like on the Tock on the actual Tock kernel code, it's extremely fast. It's like 10 to 20 seconds, and then on the interrupt code, we've gotten it down to something pretty reasonable, but that's like on the order of like 2 minutes at this point.
That's very fair. And I have a third question, but maybe I will let someone else speak before if someone has a question.
Perhaps you can quickly answer the question on the chat whether the like vanilla arithmetic overflow array specs thing runs on all the lines in the kernel. And, like whether that's included in the 10 to 20 seconds that it takes to
Yes.
verify things.
Yes, it does. Yeah. So that, just out of the box, it'll run on, every sort of function in the kernel. And I think that's actually how we found that original like underflow bug, which is kind of really cool because we didn't even have to write specifications. We had to sort through all the potential like arithmetic overflows and all that. But yeah, we didn't actually have to write any specifications to find that.
Sounds cool. Next question by Ralph.
Yes, actually, about that. So first of all, yes, definitely cool work. Thanks for sharing. Very cool stuff. So about this overflow thing, wait, you said this runs the overflow check on the entire kernel. Doesn't that mean you need to decorate the entire kernel with preconditions to ensure that all these overflows don't happen? I'm a bit confused about it. Like, you can't get overflow freedom without having specs everywhere. Right?
Yeah, that's correct. So sorry, I think maybe to like be a bit more specific, what I meant is like when you originally run Flux on something, it's going to show you all the potential areas that you have, right? Like an arithmetic overflow, right? Where that
basically every single addition.
Yeah, and then it's your job to prove that like, hey, this isn't the case. And you have to do that through adding preconditions. But I mean, there's also some places where you might not have an overflow because there's an explicit check, on the size, or the size is restricted in some other manner through the code.
Okay, I see. So you didn't, like, on the latest version with orientations, it would still report many overflows in many places because you didn't add all these preconditions everywhere, and you manually audited them, kind of.
No, sorry. So we did add preconditions. I was just trying to show like, hey, it finds these sorts of issues without you annotating anything.
But you said it's isolated like this. How can this possibly be isolated like this? This means basically every integer in the entire kernel you need to have the bounds on, or am I somehow misunderstanding something?
But yeah, I'm not sure what you mean by isolated. I think in terms, when I said isolated, what I was pointing out was like I had pulled out code from the kernel originally. And so like in our verification, because we were interested in like a very specific part of the kernel, right? It gives us like sort of a limited scope to look at. Does that make more sense?
And did you add these overflow protection preconditions only in that scope or everywhere?
In that scope, and then basically everywhere else that is relevant to what we're trying to prove about memory isolation.
Okay. Okay, so if I run Flux on the whole kernel, I still get overflow errors for all the rest of the kernel.
Yeah, you would still get
Okay.
some overflow issues.
Okay, makes sense. Thanks.
I have a question, which is maybe a bit more of the background in Tock. So the interrupt code that you showed that's written in assembly, does that call Rust code, or how does it connect to the Rust code? Or is this just only written in assembly and all interrupt handlers just must be written in pure assembly?
Yeah, so great question. Yeah, it's just written in pure assembly, and it uses the ASM macro that Rust has. And from my understanding, looking into this during this work, like that code just gets inlined into the actual, like Rust compiler's assembly, and then compiled. So there is no Rust, and it's just because these interrupt handlers have sort of like weird calling conventions. Where they're in a specific place, like at a specific address, and they work a certain way. So they're 100% assembly.
Yes, but like you could assume that I have an interrupt handler that like translates from the weird calling convention to the Rust calling convention and then forwards it to a Rust interrupt handler.
Yeah, I'm sure you could do that, but yeah. So in the Tock kernel, they don't. And I think one of the reasons is just performance. Like these things need to be as fast as possible because you have actual kernel code running, and so there's an incentive to sort of keep it as assembly.
So because otherwise my question would have been how you prove that the Rust code that the interrupt handler jumps to is correct and doesn't clobber things. But I guess if you don't have Rust code, you don't need to prove that.
Yeah, exactly. There's no Rust code there.
I see. That makes sense. I guess Sasha, you're raising your hand.
Yes. Well, last question. I remember from Nico's talk a while back also that sometimes in Flux you have to write kind of your own extensions to
Yeah.
how the types are unified or something. And my question is, as a client of Flux, because you're not developing Flux directly, I understand how many of those did you have to write? Like how much effort and how easy was that to do?
I think that was like a lot of the effort, to be honest. Um, and I wouldn't say it's necessarily hard to do, but I think it requires like, quite a bit of thought, right? And how you can do it in a way that's sound. So yeah, like there are definitely like Flux wrappers that we have all over the place so that we can, reason about like specific features. And that's like a lot of the sort of like what I'll call the infrastructure that we have in this verification project. So yeah, I would say like not necessarily hard. It's just that you have to kind of do it a lot in something that's like as large scale as the Tock kernel. And then sometimes, you need to think like pretty carefully about what you're doing.
So it could be unsound. It is part of the TCB. Those routines are part of the trusted computing base. They have to be sound separately.
They have to, yeah, they have to be. Yeah, because generally you have to sort of so like I guess maybe to give a concrete example, right? At some point you're going to have to actually write to an MPU register, right? And so this is just something that like you can write a spec for, but like it's not something that Flux can check directly. And so like yes, that has to be part of the TCB, and we have sort of ways of doing that.
Oh, thank you.
Yep.